Hello and welcome to this video on friction. Okay, so first we're going to talk about this thing mu, the coefficient of friction. Mu. Okay, so basically it's how much resistance to motion there is between two surfaces. Okay, so as I've written here, an example of a surface designed to have a low coefficient of friction is a bowling alley, and they oil the lanes to decrease the coefficient of friction between the lane and the bowling balls to make it a fun game. Okay, high coefficient of friction, bowling alley would not be fun. Okay, an example of a surface designed to have a high coefficient of friction is a climbing wall, because you want to grip onto the, like these bits. Okay, so, and also climbers put chalk on their hands to increase the coefficient of friction between their hands and the climbing wall. And here I've put a nice picture of a climbing wall in Bristol that used to be a church. Another important thing to know is that friction opposes motion. I'm sure I don't need to explain that to you. You can just think about it for a second and see why that should be true. And some more vocabulary, which is that if a surface says it's rough, then there's friction, and if it says it's smooth, as we've encountered before, that means no friction. Okay, so when you're applying a force to an object, like say this particle, you're applying, so say this is the force T you're applying, like friction only needs to push back as hard as you're pushing it. You know, friction's not going to push back more. You know, it can't be accelerating due to friction because friction's only opposing motion. Yeah, so when a particle's static, the friction is less than or equal to mu r, where mu is the coefficient of friction that we talked about at the beginning. Now, usually in a question, they'll give you that, and then r is the normal reaction force, which we've seen before. Okay, this one. Right, so that's when the particle is static. The friction's pushing back only as much as it needs to, yeah? But once it's on the point of slipping, so sometimes it will say that in a question, on the point of slipping, or if the particle is actually moving, like in this scenario, then the friction is going to be F max. It's pushing back the most that friction can push back. The most friction can push back is this, F max equals mu r. And most exam questions, you'll be using this one, not this one. Okay, now I'm going to do an example of an exam question. So let's read the question and underline the important bits. So figure 2 shows a large block of mass 50 kilograms. Okay, that's probably interesting, isn't it? Being pulled on a rough, that means there's friction, horizontal ground by means of a rope attached to the block. The tension in the rope is 200 newtons. We've got that there. And it makes an angle of 40 with the horizontal. Yeah, good. That's written down as well. Under these conditions, the block is on the point of moving. Okay, so that means the friction is F max. Okay, and now modelling the block as a particle, show that the coefficient of friction between the block and the ground is 0.424, correct, 3 SF. Okay, and it's for 6 marks, which is quite a lot. So what do we do first? We draw in the forces. Okay, so we've got the weight, 50g. We've got the reaction, R. We've got the friction, it's opposing motion. See the tension in the string, this is trying to pull it that way. Friction is trying to avoid that. So F max is going this way. And so now all we need to do is resolve this 200 because it's going in a different direction to everything else. Okay, so that's 40 degrees. So this one is 200. This is adjacent, so it's cos 40. And then going up this way, we've got 200 sine 40. Okay, so we know that because it's on the point of moving, we know that the friction is F max, but we know that it's not moving. It's on the point of moving, but it's not moving. That means that this is equal to this because it's in equilibrium. So F max equals 200 cos 40, and we know what F max is. We can use the formula that we've got written down, which is that mu r equals 200 cos 40. Right, so mu, that's what we're trying to find. R, do we know R? Let's have a look. Okay, R's up there. No, we don't know R, but we can work it out because we know this and this. Okay, we know it's not moving up or down, it's in equilibrium. So r plus 200 sine 40 equals 50g. And then if we rearrange that for r, put it into our calculator, we get r equals 361.4 ... So if at the end we might have to round our answers, but when we're during the working, we definitely want to give at least kind of 4 significant figures and then write ... to show that there's more. Okay, you don't need to write out your whole calculated display. Right, so now we found r, so now we can use that to find mu by substituting back in here. So mu is 200 cos 40 divided by r, which is 361.4 ... And if we put this on our calculators, we get 0.4238 ... Okay, so again, we're giving about 4 significant figures and then ... But now this is our final answer, and it's telling us to give our answer to 3 sig figs. So we'll do that now, because we've finished the question. Okay, 0.424236